Alright, so in this video, we're going to be talking about vibration in strings. Now, to understand better the vibration produced by strings, we need to take a look at the frequencies produced by these vibrations. And these include, we have the fundamental frequency and the harmonics, also known as the overtone. So what then is the fundamental frequencies or fundamental frequency? The fundamental frequency is the lowest possible frequency produced by a vibrating body. The lowest possible frequency produced by a vibrating body is what we call the fundamental frequency, and its symbol is F naught. Alright, so the fundamental frequency is represented with the symbol F naught. Now, to get the fundamental frequency, we consider the fundamental mode of vibration. To get a fundamental frequency, we need to consider the fundamental mode of vibration. Now, here we have the modes of vibration, the harmonics, which we are going to come to later on. And then we have the relationship between wavelength and length, relationship between speed and length, also V and L. We're going to come to all of these as we progress. Now, first, the mode of vibration. Remember, we said to get the fundamental frequency, we need to consider the fundamental mode of vibration. And for a string, this is what the fundamental mode of vibration looks like. The fundamental mode of vibration for a string starts with a node and ends with a node. Alright, it's just a stationary wave that starts with node and end with node. We know for every stationary wave, we are going to have an antinode. The antinode is located between the two nodes. All right, the node is the point of minimum or zero disturbance in the stationary wave, whereas the antinode is the point of maximum or highest disturbance in the stationary wave. All right, so the fundamental mode of vibration will have just two nodes. All right, it will start with a node and end with node. Now, basically, all the vibrations we have produced by string instruments will always have node as their beginning and node as their ending. That's to say, all vibrations produced by strings will always start with node and end with node. If you observe, for the second vibration, we have node ending with node. Third one, we have node ending with node, and so on and so forth till the last one. So all the vibrations produced by strings will always start with node and end with node. Now remember, we want to get the fundamental frequency, all right, for a string, and we said to get the fundamental frequency, we need to consider the fundamental mode of vibration, which is this. Now it starts with a node and end with node, and this is also referred to as one loop. All right, so to get the fundamental mode of vibration, we refer to make reference to one loop of vibration. All right, one loop will start with node and end with node. So this is a single loop of vibration. All right, so this is like the length of the string. It starts with node and end with node. So we can also say if from here to here is node, we can also say the length of our string. We can also represent this to be the length of our string. We can say this is L. Okay, now from our knowledge of stationary wave, we know that the distance between two consecutive nodes, that's from node to node, all right, is equal to node to node is equal to lambda over 2. All right, the distance between two consecutive nodes is equal to lambda over 2. Now, from node to node is also the length of our string. So we can see the length of our string is also equal to node, which is still lambda over 2. So we can say here that the length of our string is also equal to lambda over 2. All right. Now, if we are talking about the relationship between L and lambda, this is it here. We've gotten it. All right. Just by getting the fundamental mode of vibration. All right. This is for the fundamental mode of vibration, which should give us the fundamental frequency. All right, we have L equals lambda over 2. If we make lambda the subject of the formula, we can just cross multiply. Lambda times 1 is lambda, 2 times L is 2L. So from there, we're going to have lambda equals 2L. So this is for the fundamental mode of vibration for a string. Now, for the relationship between V and L, we know from our knowledge of wave equation that the speed of a wave is equal to the frequency times the wavelength. Now, in this case, our frequency is the fundamental frequency. Remember, we want to get the fundamental frequency from this, all right? And to get fundamental frequency, like we said, we consider fundamental mode of vibration, all right? So since we want to get fundamental frequency, we change our F to F naught. So we have the speed of sound equals the fundamental frequency times the wavelength. If we make the fundamental frequency subject of the formula, we're going to have fundamental frequency equals V over lambda. All right, that's we divide both sides by lambda, and we'll have F naught equals V over lambda. Now remember, lambda is equal to 2L. That's the wavelength is equal to L. So at that point, we're going to have fundamental frequency equals V all over. Rather than writing lambda, we have 2L. So this is the equation that relates speed and length for fundamental frequency, all right, of a string, fundamental frequency of a string. And that's why they always tell you that the fundamental frequency of a string is V over 2L. So do not forget, fundamental frequency of a string, F naught, is equal to V over 2L. All right, we got this from our fundamental mode of vibration, which is this. So write it here, relationship between V and L. We have F naught equals V over 2L. Now, the reason why I had to separate this relationship between wavelength and L, length, and the relationship between speed and length is because most times for the calculation problems that have to do with vibrations, questions usually come in two forms. It's either you're looking at a relationship between wavelength and L, of wavelength or speed and the length, all right? And this is just the equations you'll be playing around with. All right, so this is what we have here. Fundamental frequency of a string to be V over 2L. Now, we said something here that harmonics are positive whole number multiples of fundamental frequency. So if we want to talk about first harmonic, all right, first harmonic, we are going to be looking at the first positive whole number, which is 1. So we are going to have 1 times fundamental frequency, because we said it is the harmonics are positive whole number multiples of fundamental frequency. So first harmonic will be 1 times fundamental frequency, which is the fundamental frequency. So please have it at the back of your mind that first harmonic, all right, is the same thing as fundamental frequency. Now, if we want to talk about the second harmonic, now to get second harmonic, we consider 2 loops, all right, in our mode of vibration for a string. Don't forget, to get first harmonic or fundamental frequency, we made use of the fundamental mode of vibration, which consists of just 1 loop. Now, to get second harmonic, we make use of 2 loop. Now, 1 loop starts with node and end with node. To get a second loop, you continue up to the next node. That's what we have here. So this is 1 loop, all right, ending here. The second loop will continue from this node and end in another node. All right, do not forget, all strings, vibration in strings usually starts with node and end with node. So this is 1 loop and then this is 2 loop. So this is going to be for second harmonic. This is for first harmonic. So for second harmonic, we consider 2 loops. So don't forget, from our knowledge of stationary wave, we know that this point here is a node, this point here is a node, and then this point here is a node. And in between the nodes, we always have the antinodes and the antinodes. All right, so if we take this again to be the length of our string, we're going to say the length of our string is equal to 3 nodes, 3 consecutive nodes, and 3 consecutive nodes is equal to 1 wavelength. So from here, we're going to have L equals lambda. Node to node to node is lambda, and then from this point down to the string is the length of our string. All right, from this point down to this point is the length of our string. So we can say the length of our string is equal to 1 wavelength. So for the relationship between wavelength and L, we said is going to be lambda equals L. All right, if we want to get the equation for second harmonic, is simply 2F naught. All right, there are 2 ways of getting it. We either use 2, since it's second harmonic, whole number multiples of fundamental frequency, we're going to have 2F naught. Simply use 2 times V over 2L, which is going to give us V over L. or we just work with this. All right, V over lambda. All right, our lambda now is L, so we have V over L. So this is our second harmonic. Now if we want to go for the third harmonic, right? So for third harmonic, we consider three loops. So this is one loop, this is the second loop, and this is the third loop. Don't forget, a loop will always start with node and end with node, all right, for a string. So this is three loops. And from our knowledge of stationary wave, we know that this point is a node, this is a node, this is a node, and this is a node. This is antinode, this is antinode, and this is antinode. Now, three consecutive nodes is one wavelength. All right, from this point to this point is half wavelength. So in that case, we're going to be having one wavelength plus half wavelength, which is 1.5 wavelength. If we simplify 1.5, convert it from a mixed number to an improper fraction, we're going to have 3 over 2. All right, so we have 3 over 2 wavelength to be this length. All right, so this is the length of our string. So we can say in this case, for third harmonic, the length of your string is equal to 3 wavelength over 2. So the relationship between L and wavelength, we can write it here to be L to be equal to 3 wavelength over 2. This is for third harmonics. Now, if we want to get the relationship between V and L, we can just say third harmonics is 3 times fundamental frequency. All right, so we just say 3F naught. Remember, harmonics for a string are positive whole number multiples of fundamental frequency. So third harmonics will be 3 times fundamental frequency. Second harmonics will be 2 times fundamental frequency. First harmonic 1 times fundamental frequency. We're talking about fourth harmonic 4 times fundamental frequency. Fifth will be 5 times. Sixth will be 6 times, and so on and so forth. So we have 3 times fundamental frequency to be our third harmonic. So the relationship between V and L will be 3 times fundamental frequency is V over 2L. All right, F naught is V over 2L. So 3 times V over 2L, that will give us 3V over 2L. So that is for third harmonic. All right, now for fourth harmonic, we are going to be considering 4 loops. All right, this is 1, this is 2, this is 3, this is 4. This is what the mode of vibration for a string looks like. It's different from that of closed pipes and open pipes. All right, so this is 4 loops for fourth harmonic. Fourth harmonic will have 4 loops, just like third harmonic had 3 loops, second 2 loops, first harmonic 1 loop, and so on and so forth. All right, so we have fourth harmonic to have 4 loops. So from knowledge of stationary waves, we know this point is a node, this is a node, this is a node, this is a node, and this is a node. Then in between we have antinodes, 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 and antinodes. So 3 consecutive nodes is 1 wavelength. So this is 1 wavelength. All right, from this point here down to this point again, we have another 1 wavelength. So wavelength plus wavelength, that will give us 2 wavelengths. All right, so the length of this string is equal to 2 wavelengths. So for this one, we write L is equal to 2 wavelengths. All right, if we want to get the relationship between V and L, we know this fourth harmonic, we say 4 F naught. So we have 4 times F naught of fundamental frequency for a string is V over 2L. So we say 4 times V over 2L, which is going to give us 4V, all right, over 2L. If we simplify this further, we are going to arrive at 2V over L. So this is for the fourth harmonic of a string. Now for fifth harmonic, we're going to have 5 loops. Fifth harmonic will have 5 loops. All right, so this is 1, 2, 3, 4, and 5. So always start with node. We have antinode, we have node, antinode, node, antinode, node, antinode, node, antinode, and node. Now, from our knowledge of stationary waves, we know that 3 consecutive nodes is equal to 1 wavelength. All right, so from here again to another 3, we have 1, 2, 3. This is another 1 wavelength. So we have 1 wavelength plus 1 wavelength. That's 2 wavelengths. All right, now from node to node is half wavelength. So we're going to have 2.5 wavelengths. So our length here is equal to 2.5 wavelengths, which can be converted to an improper fraction to be 5 wavelengths over 2. So the relationship between L and wavelength is L equals 5 wavelengths over 2. Now for the fifth harmonic, our equation now will be 5f naught. Alright, this is fifth harmonic, so our whole number will be 5. Just like we said, harmonics are positive whole number multiples of the fundamental frequency, just a positive number. So we are going to have 5 f naught. Now don't forget, for a string, f naught is v over 2l. So we're going to have 5 times v over 2l, which is 5v over 2l. So this is for the fifth harmonic for a string. Now for sixth harmonic, we're going to be having 6 loops. So this is 1, 2, 3, 4, 5, and 6. So always starts with node. This is node, this is node, this is node, this is node, this is node. Node is simply the point of minimum or zero disturbance. Alright, so all these points are nodes. Now antinode is a point of maximum or highest disturbance. So these are the antinodes. These points here in between: antinode, antinode, antinode. Alright, so now looking at what we have here now, again, 3 consecutive nodes is 1 wavelength. So this is 1 wavelength. Alright, the whole of this is 1 wavelength. From here again to another 3 consecutive nodes, we have 1 wavelength. So from this point again down to this point, this is another 1 wavelength. So 1 plus 1 plus 1, this is going to give us 3 wavelengths. So in this case, the length of our string is equal to 3 wavelengths. Alright, so in this case now, our relationship between L and wavelengths, we have L to be equal to 3 wavelengths. Now the sixth harmonic is going to be 6 times fundamental frequency, and fundamental frequency is V over 2L. So we're going to have 6V over 2L, 6 times V over 2L. This can simplify, and then we're going to have it to be 3V over L. Alright, as the sixth harmonic of a string. Now the next thing which we are going to talk about, which is very, very important, is the overtones. Now overtones are simply frequencies that are higher than the fundamental frequency. Alright, frequencies that are higher than the fundamental frequency. Now to get the corresponding overtone, I usually advise students to go with this trick. All you need to do here is to arrange your harmonics from 1 to maybe 6 or 7. In this case, we have 6, so we can just stop at 6. So we have 1, 2, 3, 4, 5, and 6. Alright, so since we say overtones are frequencies higher than the fundamental frequency, 1 is our fundamental frequency. Alright, because here we have first harmonic to be 1 times fundamental frequency. Alright, don't forget this is for harmonics. So we have harmonics. Alright, this is for harmonics. Alright, this row is for harmonics. Now for our overtones, we're going to have overtones on this side, overtones on this other side. For our overtones, since we say overtones are frequencies higher than the fundamental frequency, first overtone is going to start from second harmonic. So we have 1, 2, 3, 4, and 5. So it simply means first overtone is higher than fundamental frequency but equal to second harmonic. Second overtone is equal to third harmonic. Third overtone is equal to fourth harmonic. Fourth overtone is equal to fifth harmonic. Fifth overtone is equal to sixth harmonic. Alright, so this is how we get the overtone. So if you're given a question, they say calculate the third overtone, you just make reference to the harmonics. Third overtone is fourth harmonic. Alright, so just do the arrangement like this. We have harmonics first, then overtones. Overtones are frequencies that are higher than fundamental frequency. So we start from 2, alright, and we proceed upward. Alright, so first overtone equal to second harmonic, second overtone equal to third harmonic, third overtone equals fourth harmonic, fourth overtone equals fifth harmonic, and so on and so forth. Alright, so these are just some of the basic things you need to know under vibrations in string. So with this, we can look at some practice problems, and let's attempt some of them now. Now in this question, they said a string is fastened tightly between two walls 24 cm apart. So let's say we have two walls. all right, and then we have a string in between them 24 cm apart, all right, 24 cm apart, that's in between the walls. So if the string is 24 cm apart, that's in between the walls, it simply means the length of the string is equal to 24 cm. Now they said the wavelength of the second overtone, we are looking for wavelength. Wavelength of what? Second overtone. Now, what's the formula for second overtone? To make things easy for us, let's relate second overtone with harmonics. So we'll come down here, we'll write our harmonics first. 1, 2, 3, 4, 5. So this is for harmonics. Now, how do we know the corresponding overtone? Remember, overtones are frequencies higher than the fundamental frequency of first harmonic. So we're going to have first overtone, second overtone, third overtone, fourth overtone. So second overtone they are talking about is the third harmonics. So now they said the wavelength of the second overtone is, we're looking for wavelength and they gave us L. So basically we're looking at a relationship between L and wavelength of what? Second overtone, which is third harmonic for a string. All right. And since they're talking about third harmonics, do not forget from the diagram we looked at previously, third harmonics will have two loops. So we have loop 1, loop 2, and then loop 3. All right, and it will always start with node and end with node. Okay, and the points of minimum or zero disturbance, we call them nodes. So these points are node also. So we have node, 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 node. Now, from our knowledge of stationary wave, we know that 3 consecutive nodes is equal to what? 1 wavelength. Okay, in case you're not aware of this, please, you can write it down. 3 consecutive nodes is equal to 1 wavelength. Node to node or antinode to antinode, all right, is equal to wavelength over 2. The same thing with antinode to antinode to antinode is also equal to 1 wavelength. Node to node is wavelength over 2. Antinode to antinode is wavelength over 2. Now, node to antinode is always equal to wavelength over 4. All right, so these are the constants we are just playing around with. All right, so from what we have here, this is third harmonic, and this is 3 consecutive nodes, one wavelength. This is node to another node. This is half wavelength. So we have 1.5 wavelength, which is 3 wavelengths over 2. All right, so from what we have here, we can see that the length of this string is equal to 3 wavelength over 2. So we have L equals 3 lambda over 2. So this is the formula that connects the length and wavelength of third harmonic for a string. All right, so now to get our wavelengths, which is what we are looking for, we simply plug in our values. We have L to be 24 equals 3 times the wavelengths, 3 wavelengths all over 2. So if we cross multiply, we're going to have 3 times wavelength, which is this is going to give us 3 wavelengths equals 2 times 24, which is 48. So our wavelengths will now be equal to 48 over 3, which is equal to 16 cm. All right, so this is our answer, option B. Now moving on, they said find the frequencies of the first 3 harmonics of a piano string of length 1.5 meter. So they give us length to be 1.5 meter. They say if the velocity of the wave on the string is 120 meter per second, so they give us V equals 120 meter per second. So we want to get the frequencies of the first 3 harmonics. And the first 3 harmonics are, number 1, fundamental frequency, 2 times fundamental frequency, and then 3 times fundamental frequency. This is first harmonic, 1 times fundamental frequency, second harmonic, 2 times fundamental frequency, third harmonics, 3 times fundamental frequency. So how do we go about this? The best way to go about this is to first calculate your fundamental frequency, which is for a string, fundamental frequency of a string is equal to V all over 2L. So we're going to have fundamental frequency equals V was given to us to be 120. All right, and L is also given to us is in meter as well. So we'll just divide 120 divided by 1.5, and that will give us 80. All right, so we have fundamental frequency to be 80 hertz. So if the fundamental frequency is 80 hertz, it simply means second harmonic will be 2 times 80, which is 160 hertz. And third harmonics will be 3 times fundamental frequency, which is 3 times 80, that's 240 hertz. So our answer will be 80, 160, and 240, which is option B. Now moving on, looking at this question here, it says the lowest note emitted by a stretched string has a frequency of 40 hertz. The lowest note is the same as the fundamental frequency. So indirectly, they are telling us that the fundamental frequency of this stretched string is 40 hertz. They say how many overtones are there between 40 hertz and 150 hertz. All right. So this is first harmonic. Now do not forget, first overtone is higher than the fundamental frequency of first harmonic. All right. So we have first overtone is higher than first harmonic but is equal to second harmonic. So basically we just write down here first overtone to be equal to second harmonic, all right, which is going to be 2 times fundamental frequency. All right, so we're going to have 2 F notes. This is first overtone. Remember the question says how many overtones are there between 40 hertz and 150 hertz. So this is first overtone. This is one of the overtones we have. So we have 2 times F naught, which F naught is 40, so we have 2 times 40, which is 80 hertz. So this is one of the overtones. Now second overtone, let's see if second overtone is going to fall in between 40 and 150. So second overtone being equal to third harmonics. Don't forget our trick here. All right, to know the corresponding overtone, just write down your harmonics. First harmonic, second harmonic, third harmonic, fourth harmonic, fifth, so on and so forth. Then for the overtones, we start from here. 1, 2, 3, 4, 5. So first overtone, second harmonic, second overtone, third harmonic. So and third harmonic for a string is 3 times fundamental frequency. Fundamental frequency here is 140. So we have 3 times. Fundamental frequency here is 40. So we have 3 times 40, which is going to give us 120 hertz. And 120 is in between 40 and 150. All right, so we have first overtone and second overtone found in between. Now let's see if third overtone, third overtone, third overtone, is third overtone going to fall in between 40 and 150 hertz. Now third overtone is equivalent to fourth harmonic. So we're going to have fourth, third overtone equals fourth harmonic, all right, which is 4 times fundamental frequency. Fundamental frequency is 40, so we're going to have 4 times 40, which is 160 hertz. All right, and 160 is above this 150. All right, so the only overtones that fell between 40 and 150 are 80 hertz and 120 hertz. All right, 80 hertz and 120 hertz, just the two of them, which is option B. So with this, we've come to the end of what you need to know as long as vibration in strings is concerned.